Hi, in this video we'll talk about smoothing orders, and in particular we'll talk about the moving average smoothing procedure. And just by definition, remember what that is. The moving average smoother takes the average of a set number of points. If it's an order 3 smoother, it takes 3 values at a time, takes the average, takes the next 3 values at a time, takes the average, and so on. So it moves one data point across, but it's taking 3 data values at a time and calculates the average of those, and in this way smooths the data. Of course, if it's an order 5, it takes 5 data values at a time. So that's the idea of smoothing data. Now, why would we want to do such a thing? Well, we have 2 main purposes to smooth the data. First of all is just to simply remove random, possibly, even probably meaningless fluctuations from a data set that gets in the way. We call it noisy data, where there's a lot of fluctuation that's going to interfere with what we're wanting to really be able to determine and analyze from the data set. So that's one reason, is to remove noisy fluctuating data and make it smoother. The second thing is, a lot of times what we would like to do is remove the cyclic piece of the data set. A data set can have a cycle, it can have trend in the same data set. And a lot of times what you'd like to do is just analyze one piece at a time. For example, you might want the trend only and to focus on the trend. Well, the problem is the cycle is in the way, and because of that, it kind of tangles up the picture and you can't really make it out to tell what everything is. So what would be nice is to have something that would allow us to remove that cyclic piece, and that's what smoothing does for us. So that's the second reason that we would like to use a smoother. So with that said, let's look at some examples in R. We'll go over there. Okay, so here we are looking at smoothing orders, and the first data set that we'll look at is the Tesla data. Recall that that is stock prices of Tesla. That ranges from January 1st through of 2020 through April 30th of 2021. So what we'll do is let's just plot it first of all and remind ourselves of what that looks like. So there is the data set Tesla. Now you can tell that it does go from 2020 up through middle of 2021, and a quick glance at the data set makes us realize, yes, it is really fluctuating. There's lots of jaggedness to the data set, and that can be troubling. That can get in the way. It can be deceiving, and we would like to remove some of that. So one way to do it is to smooth it. You can tell in the commands up above we've already done that. We called it Tesla.3, and that is a smoother of order 3. So look at the syntax that we have here, ma.smooth.wge. That's the tswge function. In order to smooth a data set, the arguments are simply the data set name, the order equals 3 here, and plot. Plot equals true, if we had said true, would take that smooth data and overlay it on top of the actual data. We've said plot equals false here because we want to look at things one at a time and not crowd the plot. So that's what the syntax is for ma.smooth.wge. Very easy to run. That's good news. And we have, first of all, just plotted Tesla. That's not the smooth data. Let's now look and see what the plot would look like of the smooth. So there's a picture of the actual. The smooth data set, what do we expect? Well, based on what we said earlier, we expect it to remove some of that fluctuation. And look at this picture. You can see that, yes, it did. Really, it's the same look. Order of 3 is not very high. So all it really did was it just shaved off that fluctuating piece, and otherwise looks pretty much the same. Well, what happens when you go up a little higher, as in order 8? So if we look at an order of 8, it's going to even remove more of that fluctuation and look like this. So that makes sense. It's just showing us that the higher the order, the more the smoothing. Let's do the same thing for DFW.year. Recall that that is temperature data for Dallas-Fort Worth area. It's the average annual temperatures from 1900 to 2020. And we can tell when we look at this, let's go ahead and plot it as we did last time for Tesla. What do we see? Well, we see quite a bit of fluctuation. That would be year-to-year variability. You can see this goes from 1900 out to 2020. Quite a bit of fluctuation in between the years. Sometimes the highs are really high, sometimes the lows are really low, and it's really all over the place. You can tell just with your eyes that there towards the end, after 2000, it does make you wonder if there's a trend going upward. And we'll be talking about that in other parts of the book, and we'll be studying that in more detail later. But for now, we can just smooth it and get some information. So let's do the same thing we did last in the Tesla data, and let's look at a smoother of order 3. Run that. What do you expect? We expect that some of that fluctuation to disappear. And that's what we have. Still quite a bit of up and down variation. Let's go to a higher order, as in 8. What do we expect now? Well, we expect even more of this fluctuation to be removed. And we have this. Here it's really apparent, looking over here, that from years about, let's call that 85-ish up to year 110, a really pretty consistent trend upward. Then after that, it looks to have settled a little bit, at least flattened. So that's interesting look there. But there is a good example of what smoothing can do for us. Let's go to another example and look at what we call a cosine plus line plus noise model. So there'll be 3 components to this model. First of all, what we'll do is we'll let time go from 1 to 60, and then we're going to create a cosine curve with period 10. Hang on to that, that's going to be important. A cosine curve with period 10, which simply means it takes 10 time points in order for it to complete its cycle. Then we're going to also make a line, just a regular y equals mx plus b line, where our x is really t, as in time. And then we're going to sum those up and make it a cosine plus line. Then we're going to create some noise, random noise, given by the function rnorm. Rnorm creates normal random variables with a mean of 0 and a standard deviation of 1. We didn't have to put SD equal 1 in there because it is the default. And then we're going to add those and call that x. So cosine plus line plus z. So let's do that first. Let's just run that piece. We won't get any output from that, but just to get that set, run that. And then what we'll do is using the MF row for multi-frame row-wise layout, we'll do a 3x3 layout so we can easily compare. We're going to plot each of those pieces up above. Now remember, the type equals L just means line. We're only going to have one of those. It'll be on the actual line. The others are going to be a type of O, which says we want it to type the plot to show the plot to the points on top of the plot. Okay, so let's take a look, run it, and see what we have. Upper left is the plot of the cosine curve. You can see that it takes 10 points in order to complete a cycle. Plot B is a plot of the line. Plot C is the sum of the cosine plus the line. So it's the plot of plot A plus plot B. So we can call it an ascending cosine look. Then plot D is the plot of the noise. That's the Z. And you can tell it's a mean of 0. The standard deviation of 1 comes into play. You can tell by the ups and the downs about how high and how low it goes. And then if we were to combine plot A plus B plus D, we end up with plot E. Now, if you were just to look at plot E, and that's our actual data set that we're going to work with here, you would wonder, well, you might be able to see that it's increasing upward. That seems pretty obvious. But wow, there's a lot of fluctuation. Why is that fluctuation? It's because of this noise back here in D. But you might wonder about the cycle. Not sure about the cycle because it's been obscured by all that noise. Well, again, what's smoothing good for? Smoothing is good for letting you take a look at the cycle, and if you wanted to remove the cycle, or how about this, remove the fluctuations from the data so you can see the cycle. That's one thing. So let's see what happens here. We're going to look at this order of 5. So we did a smoothing average MA, moving average smoother, of order 5. And look what it shows us. Now here we did say plot equals true because we wanted to overlay the plot, the smoothing data on top of the actual data. And what do you see? You see here that we can see our cosine curve. So you can recognize, remember plot C was the signal. That was the cosine plus line piece of the data without the noise. That was the true signal. But plot E was really hard to recognize because of the noise. And what plot F has done for us is removed that fluctuation to where what we can see now is the original signal. And that's valuable. Now, I'm going to do one extra little thing here. Let's let the order be 10. Now remember that this cosine curve had a period of 10. And remember that the two uses for smoothing, the first one was to remove potentially meaningless fluctuations from the data, just like we did with an order of 5. But remember that a second purpose for smoothing is to remove the cyclic behavior altogether, leaving us with just a trend. Watch what happens when we run the command with order of 10. Now the smoother has no cyclic behavior in it at all, and it's just left us with the trend, which looks a lot like plot B. Now, why did it work for plot G and not for plot F? Plot F showed the cosine curve, the cosine plus line piece. But whenever we took the order higher, up to 10, it completely got rid of the cosine and just left us with the trend, that is the line. Why was that? Well, it's not coincidental that it's because the order matched the period. Recall that the period of this cosine curve was 10, and we did a smoothing, MA smoother of order 10. And when you do that, you completely eliminate the cosine behavior, the cyclic behavior, and you're just left with the trend piece. So that's a really good illustration of how that works. Okay, let's do one final example. We're going to look at air passengers data, very popular time series data set, just in general and in our book too. So let's look at a plot of the air passengers data just to review ourselves of what that looks like. Recall that this data set, it wasn't a real long data set, maybe 1948 up through about 1961 or so. And what do we notice about that? Well, first of all, it's got an increasing trend about it. And secondly, we see that the fluctuations, that is the peaks and the troughs, seem to be more and more extreme as time goes on. We call this a multiplicative model as opposed to an additive model. And we've talked about that before, but that is the air passengers data. Now, what if we were to smooth this? And let's talk about an order of 5, 9, 12, 15, and 18. And you'll see why we've chosen those orders. First of all, let's recall something. Recall that the air passengers data has a cycle. It's not sinusoidal. Those certainly don't look like sine or cosine curves. But it's definitely on a 12-month cycle, meaning that each January behaves a lot alike, each February behaves a lot alike, and it takes the calendar year before it repeats itself. In other words, it's got a period of 12. So what are we expecting based on the last example where we had the cosine with period 10, and when we had order 10, what did it do? It removed the cyclic component. Let's see if that happens to us here. First of all, we'll start lower than an order of 12. We'll look at an order of 5 and see what that looks like. And indeed, it has removed some of the fluctuation. It's trimmed off those really tall peaks, and it's And the same for the low troughs. Let's look at an order of 9. Even more so. Let's go to order of 12. Now remember, this order is matching the period. So what do we expect? We expect for all of the cyclic component to be removed. That's exactly what we have. And what it's showing us is the trend line. Now, you might wonder, well, I wonder what would happen if we go up to order equal 15. Well, and I'll just admit that what I would think logically is, wow, this is going to really straighten this line out. But I'm going to be wrong by that. Let's take a look. If you look at order 15, lo and behold, it introduces some of that cyclic behavior again that was in the original data set. So there's a point of diminishing returns. If you make the order exactly equal to the period, that does remove all of the cyclic behavior, or most of it, and leaves you with a great estimate of the trend. But if you go any higher than that, it starts to introduce some of the old cyclic behavior again, which is a very strange result. It's unexpected to me anyway. Brings up another question. What happens if we go to order 18 and you just get more of the same? So that's an interesting result, really neat, and it illustrates the idea of smoothing. And really the big takeaway is whenever a data set has a period of a certain value, like period 12 or period 10, if you do a moving average smoother of that same order, that where the order equals the period, what that does is that removes the cyclic component and leaves you with the trend. And oftentimes that's what we're wanting to do, is estimate the trend and focus on the trend. So that's one of the big uses of smoothing. The other one, of course, was just in general to remove fluctuations from a noisy data set so you can get a better picture of what you're wanting to see. But anyway, very valuable stuff. I hope you enjoyed that, and looking forward to the next video.